Lift up my eyes to the hills, I'm blessed, oh man. Sometimes I'm lost and far from home, but I'll find my way. I follow my heart, I know I'll be found someday. While I'm lost, I learn and live. What do you say? Let's have a good time until that day. Oh, every morning I rise, I stare at the sun. I know it is a blessing. So when the evening comes, I lift up my eyes to the hills, I'm blessed, oh man. With my two hands in the air as far as I can. Lift up my eyes to the hills, I'm blessed, oh man. With my two hands in the air as far as I can. Yeah, as far as I can. I can, yeah. My two hands in the air as far as I can. When I look at where I'm coming from, I know I'm blessed, and I close my eyes and smile. Sometimes I feel like the richest man in Babylon, and I've done my best, so everything's alright inside. Oh, every morning I rise, I stare at the sun. I know it is a blessing. So when the evening comes, I lift up my eyes to the hills, I'm blessed, oh man. With my two hands in the air as far as I can. Lift up my eyes to the hills, I'm blessed, oh man. Sometimes I'm lost and far from home, but I'll find my way. I follow my heart, I know I'll be found someday. While I'm lost, I learn and live. What do you say? Let's have a good time until that day. Oh, every morning I rise, I stare at the sun. I know it is a blessing. So when the evening comes, I lift up my eyes to the hills, I'm blessed, oh man. With my two hands in the air as far as I can. Yeah, as far as I can. Lift up my eyes to the hills, I'm blessed, oh man. With my two hands in the air as far as I can. Yeah, as far as I can. I can, yeah. My two hands in the air as far as I can. When I look at where I'm coming from, I know I'm blessed, and I close my eyes and smile. Sometimes I feel like the richest man in Babylon, and I've done my best, so everything's alright inside. Oh, every morning, I rise, I stare at the sun. I know it is a blessing. So when the evening comes, I lift up my eyes to the hills, I'm blessed, oh man. With my two hands in the air as far as I can. Stare at the sun, I know it is a blessing, yeah. Lift up my eyes to the hills, I'm blessed, oh man. Ooh. Sometimes I'm lost and far from home, but I'll find my way. I follow my heart, I know I'll be found someday. While I'm lost, I learn and live. What do you say? Let's have a good time until that day. Oh, every morning, I rise, I stare at the sun. I know it is a blessing. So when the evening comes, I lift up my When I look at where I'm coming from, I know I'm blessed, and I close my eyes and smile. Sometimes I feel like the richest man in Babylon, and I've done my best, so everything's alright inside. Oh, every morning, I rise, I stare at the sun. I know it is a blessing. So when the evening comes, I lift up my eyes to the hills. I'm blessed, oh man, with my two hands in the air as far as I can. Sometimes I'm lost and far from home, but I'll find my way. I follow my heart, I know I'll be found someday. While I'm lost, I learn and live. What do you say? Let's have a good time until that day. Oh, every morning, I rise, I stare at the sun. I know it is a blessing. So when the evening comes, I lift up my eyes to the hills. I'm blessed, oh man, with my two hands in the air as far as I can. Lift up my eyes to the hills, I'm blessed, oh man, with my two hands in the air as far as I can. Yeah, as far as I can. I can, yeah, my two hands in the air as far as I can. When I look at where I'm coming from, I know I'm blessed, and I close my eyes and smile. Sometimes I feel like the richest man in Babylon, and I've done my best, so everything's alright inside. Oh, every morning, I rise, I stare at the sun. I know it is a blessing. So when the evening comes, I lift up my eyes to the hills. I'm blessed, oh man, with my two hands in the air as far as I can. As far as I can. stare at the sun. I know it is a blessing. Yeah. Lift up my eyes to this, I'm blessed, oh man. Sometimes I'm lost and far from home, but I'll find my way. I follow my heart, I know I'll be found someday. While I'm lost, I learn and live. What do you say? Let's have a good time until that day. Oh, every morning I rise, I stare at the sun. I know it is a blessing. So when the evening comes, I lift up my eyes to this, I'm blessed, oh man. With my two hands in the air as far as I can. Lift up my eyes to this, I'm blessed, oh man. With my two hands in the air as far as I can. Yeah, as far as I can. I can, yeah. My two hands in the air as far as I can. When I look at where I'm coming from, I know I'm blessed, and I close my eyes and smile. Sometimes I feel like the richest man in Babylon, and I've done my best, so everything's alright inside. Oh, every morning I rise, I stare at the sun. I know it is a blessing. So when the evening comes, I lift up my eyes to this, I'm blessed, oh man. With my two hands in the air as far as I can. Stare at the sun, I know it is a blessing. Yeah. Lift up my eyes to this, I'm blessed, oh man. Sometimes I'm lost and far from home, but I'll find my way. I follow my heart, I know I'll be found someday. While I'm lost, I learn and live. What do you say? Let's have a good time until that day. Oh, every morning I rise, I stare at the sun. I know it is a blessing. So when the evening comes, I lift up my eyes to this, I'm blessed, oh man. With richest man in Babylon, and I've done my best, so everything's alright inside. Oh, every morning, I rise, I stare at the sun. I know it is a blessing. So when the evening comes, I lift up my eyes to this, I'm blessed, oh man. With my two hands in the air, as far as I can. Sometimes I'm lost and far from home, but I'll find my way. I follow my heart, I know I'll be found someday. While I'm lost, I learn and live. What do you say? Let's have a good time until that day. Oh, every morning, I rise, I stare at the sun. I know it is a blessing. So when the evening comes, I lift up my eyes to this, I'm blessed, oh man. With my two hands in the air, as far as I can. Lift up my eyes to this, I'm blessed, oh man. With my two hands in the air, as far as I can. Yeah, as far as I can. I can, yeah. My two hands in the air, as far as I can. When I look at where I'm coming from, I know I'm blessed, and I close my eyes and smile. Sometimes I feel like the richest man in Babylon, and I've done my best, so everything's alright inside. Oh, every morning, I rise, I stare at the sun. I know it is a blessing. So when the evening comes, I lift up my eyes to this, I'm blessed, oh man. With my two hands in the air, as far as I can. Stare at the sun. I yeah. Lift up my eyes to the hills, I'm blessed, oh man. Sometimes I'm lost and far from home, but I'll find my way. I follow my heart, I know I'll be found someday. While I'm lost, I learn and live. What do you say? Let's have a good time until that day. Oh, every morning I rise, I stare at the sun. I know it is a blessing. So when the evening comes, I lift up my eyes to the hills, I'm blessed, oh man. With my two hands in the air as far as I can. Lift up my eyes to the hills, I'm blessed, oh man. With my two hands in the air as far as I can. Yeah, as far as I can. I can, yeah. My two hands in the air as far as I can. When I look at where I'm coming from, I know I'm blessed, and I close my eyes and smile. Sometimes I feel like the richest man in Babylon, and I've done my best, so everything's alright inside. Oh, every morning I rise, I stare at the sun. I know it is a blessing. So when the evening comes, I lift up my eyes to the hills, I'm blessed, oh man. With my two hands in the air as far as I can. Stare at the sun, I know it is a blessing, yeah. Lift up my eyes to the hills, I'm blessed, oh man. Sometimes I'm lost and far from home, but I'll find my way. I follow my heart, I know I'll be found someday. While I'm lost, I learn and live. What do you say? Let's have a good time until that day. Oh, every morning I rise, I stare at the sun. sun. I know it is a blessing. Yeah. Lift up my eyes to the hills, I'm blessed, oh man. With my two hands in the air as far as I can. Yeah. As far as I can. I can, yeah. My two hands in the air as far as I can.
Explanation of exactly what machine learning is. We can think of it as the science of giving computers the ability to learn automatically. Or in simpler terms, it allows computers to act like humans. It improves the learning as they encounter more data. Our guest speaker, Victor Dibia, is currently a principal research software engineer at the Human AI Experiences, also known as HAX, team at Microsoft Research. His research interests are at the intersection of human-computer interaction, computational social science, and applied machine learning. His research has been published at conferences such as EMNLP and CHI, and has received multiple Best Paper awards, and also been featured in outlets such as the Wall Street Journal and VentureBeat. He's a senior member of IEEE, a Google certified professional, and currently a Google developer expert in machine learning. He holds a PhD in information systems from City University of Hong Kong and was also awarded the Hong Kong Research Grants Council. So, no further ado, I'll turn over to Victor so he can do what he does.
Um, hi everyone. Hi Hakeem. Thanks for that introduction. I wish the introduction wasn't that long because what I really want you guys to see me as is just another student just like you. And I think one of the most important parts of my career was that, or has been that I always see myself as a student and I'm always constantly learning. And believe it or not, a few years ago, or maybe many years ago, I was just a student just like you guys and there were a lot of things that I just didn't understand. So I guess the most important thing that I'd like you guys to take away from this is that if there are things that you don't understand, if there are any of the topics I talk about today that are not clear, the excellent way to bridge that gap in knowledge is just to ask questions. And so, like Hakeem mentioned, today I'll talk about a bit about introduction to TensorFlow. I know that your organizers, Hakeem and Gemma, they let me know that you guys have done some introductory courses, and so you guys have some background. But that notwithstanding, just let me know if there's anything that's unclear, and if there's any questions that you have, please feel free to share them in real time. Okay. With that being said, a bit about my background. I think Hakeem has mentioned all of that. And so what I want to also mention is that I'm really passionate about community, and it's really great to be with a group of students just talking about machine learning and just talking about ways to apply machine learning to solve problems. And so that's one of the things that I really have get a lot of excitement and enjoyment from. So talking with members of the community like you guys, students. And so, as with regards to today's agenda, the main here's what I plan to cover. And so the first is what is machine learning? Just giving a broad distinction between. So, for example, you might have heard people refer to this space as artificial intelligence. Some may talk about machine learning. Some may talk about deep learning. Just to discuss a bit about the differences between these three areas, how they're related, that sort of thing. Um, then I'll talk about TensorFlow. Just talk about why or what TensorFlow is all about, why it's important, and the sort of benefits you get from using a library or a framework like TensorFlow. And then I'll talk a bit about TensorFlow Hub, which is like a repository where you could get a set of pre-trained models. So essentially, a bunch of really smart people have gone and they've trained some deep learning models mostly that solve a specific task. And the goal is that you could either use those models the way they are to solve your specific problems, or you could take them and then improve them to solve like some adjacent or related problems. And then finally, I'd like to leave some time to discuss any topics you guys might be interested in. And so I know that one of the hardest things in machine learning, at least when I got started, was to figure out how I could take a problem and then frame this problem as a machine learning problem, and then figure out the right tools, the right techniques, the right models to use to solve this problem. I know that the platform that we have seems a bit one way, and so I don't know what the best way to get feedback from you guys is, but Hakeem, generally, what's the easiest way for participants to sort of ask questions in the middle of the presentation?
I think they can. Akim?
Okay. So just for everyone, if you do have questions, put it in the chat. There's no such thing as a stupid question. Every question is important as long as it helps you understand the topics that are being discussed. Okay, so the first area I'd like to talk about very informally is what is machine learning. So let's review some terminology. And so the first interesting thing to the first set of distinctions to be able to make is that you can think of artificial intelligence as like a broad topic, and within artificial intelligence there's machine learning, and then within machine learning there's deep learning. And so what is artificial intelligence? So broadly is this field that describes any effort to make machines intelligent, or enable machines to have like perceptive and cognitive capabilities like human beings will have. And so, typically there are a set of tasks that are typically, you would use a calculator. There's some tasks that like are really, really well specified. And so for those set of tasks, machines, computers work really, really well. And then there's the other set of tasks, like things like understanding the content of, let's say, language, describing the content of images. So this sort of tasks, typically they used to be only within the limits of just human beings. Only human beings could solve tasks like that. And so the whole field of artificial intelligence just describes any effort that tries to like enable machines perform tasks that usually require some sort of perception, cognition, and reasoning. And these are tasks that typically machines couldn't do. And so it's a really old field. It's as far as the 1940s, there were people publishing papers and sort of showing progress in this area. The next sub area of this field is machine learning. And so machine learning is sort of lower down the stack. And so we are looking at algorithms that enable machines independently learn from data and make predictions. And so to give a really simple example of how machine learning sort of flips the paradigm of how you build programs or how you solve problems. Maybe 15 years ago, 20 years ago, if you had to create an application that, let's say, you give this application an image and it has to solve this perceptive task of, say, telling you what animal was in that picture, in that image, then one of the things you would do was that you will take your image and let's say you'll convert it into a series of pixels. So the pixels are just a binary representation of images. So zeros and ones or 0 to 256, depending on the format that you use to represent your image, depending on if it's black and white or RGB. And after you had that, you will then write a bunch of rules that will sort of look at this image and sort of try to figure out, let's say, if you're trying to figure out if it's a cat, you probably might look for pointy ears within the image, and maybe you might look for whiskers. And you will have to specifically write rules and heuristics or filters that sort of try to find these features. And then based on the results of these filters, you might then decide if it's a cat or a dog. So in this case, maybe if you're trying to distinguish between a cat and a dog, you would say, oh, if my filters find 2 pointy ears, then it's a cat. And if it doesn't, it's a dog. And so that was sort of the previous paradigm. And so you have your rules that you have written, and then it goes into your computation platform, and then you get your label out. And so the opposite is the case with machine learning, where rather than write the rules of what it means for an image to contain a cat or dog, what you do instead is that you generate a large data set. And so in this case, maybe you might go and collect a data set of 100,000 dogs and 100,000 cats. And you then get an algorithm to look at these two different sets of images, and then try to automatically distinguish what does it mean for something to be a cat, what does it mean for something to be a dog, and how can I link these features that I'm discovering to the labels. And so examples of algorithms in this space are decision trees, random forests, reinforcement learning methods, and more importantly, deep neural networks. And so that brings us to like this final piece, which seems to be the most interesting and important piece in artificial intelligence these days, which is deep neural networks. And so deep neural networks are just a class of machine learning algorithms. Again, they follow this paradigm of trying to learn independently from data. And so essentially you have your data, you have labels, and the goal is to learn from all of this data independently as opposed to explicitly designing rules. However, there are a few differences. And so the biggest difference is that you can think of deep neural networks as a set of stacked computation units. And so computation here means just maybe some sort of mathematical operation. And so it's like multiplications, divisions, things like that. But they're stacked in this way, and there's several of them. And so the word deep comes from the fact that like there's several of these computations where the output from one set of computations flows into the input of the next set of computations. And that's what gives us the idea of deep neural networks. And then some of the properties of DNNs, or deep neural networks, is that typically they have very high accuracy. And so if you have enough data, then you get even better accuracy. There's been a lot of advances in this space in the last 10 years. And because of how these computations are stacked, you can run them in parallel on GPUs. And so they run very, very fast on GPU computation accelerators. Any questions so far? Let me check. Okay, none yet. And so for the rest of this talk, most of the time, I mean, given that we're talking about TensorFlow, most of the time when I mention artificial intelligence or machine learning, what I'm really talking about is deep learning. So it's this class of stacked computations. I know that you guys have had some background introduction to machine learning, but I just want to reiterate what a single computation in a deep neural network typically looks like. And so there are a few components. And so the first is, for each of those computations, you will probably have a list of inputs. And then for each of these inputs, there are a set of weights. And the weights are how you sort of tune the operations that are performed on the inputs. And then finally, these inputs, they are multiplied with the weights. And then there's a sum, and there's some constant value, which is called the bias, that's then added to it. And then this result is passed through some activation function, which typically is some sort of nonlinear function. So in some cases here in the diagram we're looking at, it's just a simple if the result of this multiplication of inputs and weights and sum, if it's greater than 0.5, then I output a 1. And if it's less than that, I output a 0. Yeah, and depending on how you define that activation function, then your model might behave differently. So examples of activation functions are a tan function, a ReLU function, this sort of things. And so it turns out that when you take these functions and you sort of chain them, you put them next to each other, where the output of one flows into the input of the next set of functions, then it turns out the more interesting thing is that when you arrange these functions in this manner, you can then approximate any type of function. And so I know this whole concept might need a bit more time for you to get familiar with, but one interesting thing that you can sort of, one interesting way to reason about why we want to chain multiple functions here is that depending on the problem you're trying to solve, the problem may be easy. In one case, it's a linear problem, or it may be very, very complex, in which case it's a nonlinear problem. And so it turns out that if you stack all of these functions together, and because of the nonlinear activation functions, you then get this overall function that can be complex and can fit multiple complex spaces. In terms of terminology, the thing that goes into your stack of networks, you think of it as your inputs. All of the independent, all of the layers between the input and the output, you call them hidden layers. And then finally, you have like two outputs that sort of correspond to the nature of the problem. And so let's say if you're interested in classifying between two types of animals, a dog and a cat, then you have two outputs where if there was one output representing cats, and so each time you have a pass through the network, that output will be high, have a high value, and the other one will be low, and vice versa. Before I go down to talk about TensorFlow, I think there are two things I wanted to just refresh your memory on. And so it's the idea of machine learning models and them being in different phases. And so the first phase of any machine learning model is the training phase. And so initially you have this model, and let's say you have its parameters or its weights, and those things are set to some initial random value. And the goal is to show this model all of your data, and then it uses this data to figure out how to update its weights such that when it makes predictions, these predictions are correct most of the time. And so this sort of phase is called the training phase. So it's just the process where, you know, the model sort of looks through the data that's available, and its parameters are updated such that it's more likely to get the correct answer. After you have your training phase, you then have your test phase. And so typically you want to take some data that the model has never seen before, and you want to tell it, oh, you know, here's this new set of 20 cats and 20 dogs that we haven't seen while we were training. Now try to predict which of these are dogs and cats. And so that way you can then say, oh, you know, if it gets all the cats right and it gets some of the dogs right, you can then compute a measure of the accuracy of the performance of the model. And then finally, there's a prediction phase where, you know, now you have this application. Let's say you've become very, very famous and you've built a company. And now part of this, what this company is doing is that it's looking at all the images on Instagram, and it's assigning labels or tags to them. And so now in this phase, you have this, each time someone uploads a user uploads a new picture, then your model then could assign some sort of tag or make some sort of prediction. And so it's sort of good to think of all these phases. Of course, there's still a few different phases in between. So for example, there's validation, where you probably train multiple models and you want to validate the performance of all of these multiple models. There's monitoring, where, let's say, as it, while your model is in production, you want to monitor if this performance is still stable or if its performance is degrading. And then there's model updates, fine tuning. There's a lot of other phases, but on the high level, these are three different phases that you will typically have a model go through. Um, One of the other questions that I wanted to cover was related to um, how you might build a good predictive model, right? And so I know that some of you are working on projects. There's a challenge that you guys are working on. Hakeem, generally, do you want to remind me of what that project was again?
Oh, okay. So there is a solution challenge. I
Yep.
mean, you have different person working on
Yeah.
various projects. So I'm not sure what each person would be
Yep.
working on each group.
Yeah.
But
Yep.
I think this could be implemented
Mhm.
as well if it is that they need to
Yeah.
predict any form of,
Mhm.
you know.
Yep. Yeah. So thanks for just sort of reminding everyone about that. So one of the challenges that you might face when you start to figure out what project you want to work on is, will machine learning be a good fit? Will a machine learning uh, based approach be useful for this specific problem that I'm thinking about? And the one of the approaches that I find very, very useful for thinking through this process is just applying the scientific method. So, step one, number one, you sort of define your goal. So, you define what your research goal is. So, maybe you want to predict, I don't know, the chance of infant mortality, or you want to predict the chance of a person having an eye disease, or you want to predict if like a plant has some sort of disease on it. The goals might vary. So, or maybe you want to predict how heavy traffic will be on a given day. So, like, say you want to create like a weather prediction model. So you set your research goal. The next thing, you make a hypothesis. So essentially, this is the part where you start to think like an expert who is going to solve the problem. And so, typically, if you met like someone that works at the weather station, and you randomly ask them, oh, like, um, what do you think the weather is going to be tomorrow? And so I think you can then start to think of things like, the person might say, oh, yesterday it was rainy, so maybe it's more likely today is going to rain. Or yesterday the temperature was X degrees, so I think it's going to be just maybe yesterday's temperature, but maybe a little warmer, a little colder. So essentially, um, you can think of all the ways a human might approach the problem, and then try to collect data, because all of that data might be useful to solving the problem. So in this case, if you're going to predict how heavy traffic will be on a given day, you can make a hypothesis that, instead, the weather might be an informative signal. Maybe it might matter if it's a public holiday, because maybe public holidays, there's less people going to work, so traffic will be less. It might matter that the day of the week, um, maybe on weekdays, people are going to work compared to weekends. It might matter the season, maybe given the season, maybe events, all of that. And so all of these thought process can come together as part of your hypothesis, and you decide if you have enough signal to actually make a prediction. The third part is, once you've decided about all of these features and potential hypotheses, you then collect data to reflect those things. Then once you have all of that, you then say, okay, I have all this data. Are they actually useful in training a model that correctly predicts traffic? And so you train a model, and then you analyze your results. Then you sort of figure out, is the model better than some existing system? So maybe the existing system was like, people will predict that like tomorrow's traffic will be exactly the same as today. So that could be a baseline. And then you figure out if your model is better. And then finally, you draw a conclusion. Say, okay, if this model was worse than the previous baseline, maybe I shouldn't use it. And if it was better, maybe I should use it. And then finally, you can then refine your hypothesis, maybe figure out that the model didn't behave well. Maybe it's because there's some data that I just didn't have, and I need to figure out how to collect more data. And so this is just a really good framework on how to think through solving problems as you look at your solution challenges. And then when it comes to implementation, there are three areas that I think will be useful for you to think through again. And so the first thing is, um, does the data I have contain sufficient signal to solve the problem? And so, for example, if you're going to predict if a person has eye disease, a good way to think about it would be, how might an optometrist solve this problem? So typically what the optometrist will do is that they will probably use some sort of lens or device to take a picture of the person's eye and then look at this picture and then sort of determine if there's some sort of eye disease going on. What you don't want to do is maybe imagine that you could look at the person's sleep data. If maybe they slept 4 hours, if they sleep 4 hours per night, maybe this might mean that they have disease, eye disease. And so typically it's easy to fall into this trap where you might just not have access to the right data that that logically might be useful in predicting an outcome, and then try to look for other data. So typically one of the biggest mistakes you could make would be to not have the right data. So it's always a good idea to think of what would an expert sort of do in order to solve this problem. The next thing to think about sort of needs a bit of domain knowledge, but if you're not very familiar with machine learning, the way to solve this would be to sort of describe your task. Think of it, what type of task is it, and then maybe search in Google to figure out how other people have solved this sort of task. And so, for example, is my problem a classification or regression problem? And so classification here is that you have a discrete set of outcomes and you want to predict one of X outcomes. Regression is like you want to predict the continuous value. So for example, in the classification case, you have images and you want to predict if it's a dog or a cat. So that's a classification problem. And regression is like, hey, you want to predict the price of a house. And so that's more of a continuous value. And typically you want to use the right model type for the right sort of problem. Another thing you can look at is time, the time component to some problems. And so some problems are time series problems. And so let's say forecasting the weather, these sort of problems have a time component to them, and you need to use temporal models for that. So you hear things like recurrent neural networks, you hear things like, I don't know, time series analysis and forecasting tools, that sort of thing. And that's sort of different from static problems where data conforms to this like independent and identically distributed requirement. The third has to do with the complexity of the problem. Some problems are simple, and so these are linear problems. And so you can use a much simpler model like linear regression to solve those problems. Other problems have a much more complex problem space and you need like really complex models. So for example, understanding content of images, pretty complex space problem. And so you would need like more complex models like deep neural networks or something that like does a really good job of separating of features that some sort of feature extractor that separates, sort of converts the problem from the complex space to the linear space. And then finally, if you have the right data and you have the right type of model, the final thing is how can I tune or update my model? How can I just continue refining it till it gets better? So you want to increase your accuracy, you want to reduce your loss or your error, that sort of thing. You want to try multiple models, do some sort of change all the hyperparameters so you find the hyperparameter that works really well. So with all of that background out of the way, let's talk a little bit about TensorFlow. And so why do you need TensorFlow? And so first of all, TensorFlow is a numeric computation library. And so if you heard me talk about all the things I talked about, you know, deep neural networks, they are a chain of stacked computation. And essentially you have all these weights, you multiply them by your input, you sum all of that together, you add a bias, you pass it through an activation function. To implement that in practice, it does take, you will need to write quite a bit of code if you're going to implement that in practice. So the good part is that with a library like TensorFlow, there are really, really nice high-level abstractions where with, let's say, 2 or 3 lines, you could implement a neural network as opposed to writing, let's say, 100 lines of code to manually do the same thing. And so to make a neural network work, you need to do a lot of matrix operations, and so multiplying your inputs by your weights, and so these are matrix operations. And then to sort of update the parameters of the model as you train, um, you would need things like differentiation, back propagation. So these things can be complex, quite complex to implement by hand. And so TensorFlow helps you do all of that pretty easy, and I'll show some examples. The other good thing is that TensorFlow provides several high-level abstractions, and so if you're not really concerned about the low-level implementation, um, which I think is the use case for most people, so I rarely ever have to go to the low level to implement anything in TensorFlow or in applying neural networks in general. And so there's this nice high-level abstraction that it provides, and so there's the TensorFlow API, the core TensorFlow API. There's also the Keras API, which some of you might have heard about. And so I definitely recommend you to use the Keras API. It's sort of user-friendly, designed to be as user-friendly as possible. So um, it's also high performance underneath. It's based on C++ binaries, which run really fast. Then finally, the ecosystem of like tools for TensorFlow is really, really mature. So for example, you could write TensorFlow code that you can run in the browser in JavaScript, which is one of my favorite things to do. And you can compile your TensorFlow models and run them in TensorFlow Lite on mobile devices on your mobile phone. And then you can just host them on the server in Python. And so this is one of the good the benefits that I think of TensorFlow. And before I go any further, I'd like to just show some example, just a really quick example of something, some example tool that I have created to demonstrate how you might use TensorFlow machine learning to implement an image search system. Let me do a quick screen share. Right, and so I'm going to put a link to this application. It's a web application, and you guys can play around with it later. Let's see, let me go to the general or Q&A. Can you guys see that link? Can someone just confirm that you can see the link to this? Excellent. And so, so you probably have seen that Google has this feature. I think if you go to images.google.com and you look for image search, you could upload an image and then Google will tell you, oh, here are all the images I think are most similar to this image. And I think there are many other tools or applications that have this sort of functionality. So underneath, the problem is called semantic image search. And so in this case, you don't have any text description of images. You don't have any metadata. All you just have is the image itself. And you want a machine learning model to look at the content of these images and tell you which image is similar to the other. And so in this demo, I have 200 images here. I think most of them are like several categories. So cars, banana, the Eiffel Tower, this sort of thing. And if I selected one of these, like a banana, then some machine learning model underneath shows me all of the images from the same data set that are most similar to the thing that I selected. And so if I select this truck, it gives me all the other trucks that are most similar. And if I selected this tractor, it gives me all of the other things that are most similar. And so underneath, how does this work? So essentially what happens is that you get a machine learning model, a pre-trained model, like let's say ImageNet. I don't know if you guys have heard about them, but you can get this model to extract features from each of the images. And so you pass this image through the network and it outputs a set of numbers, which we'll call embeddings or just vectors. It's essentially just a list of numbers. But these numbers are sort of important such that it codifies what it means for an an image to belong to a particular class. And so if you have numbers for all of the images, you can then say, okay, given the numbers for a specific image that I've selected, show me, and given the numbers for all the other images in the data set, we can then look at like a distance metric. So we'll do some like cosine distance, or we can look at the distance between these metrics and sort of figure out which ones are similar or not. And underneath, if you wanted to figure out a bit more how this model works, so you could sort of figure out if I use different model architectures, let's say mobile net model architecture, efficient nets, dense nets, and I use features from different layers in this model, how might this system behave? So this is just a demo I created a while ago, just to make it a bit interactive for people new to machine learning, sort of visualize if I was going to build a search system and I used a pre-trained model, say any of these models here, and I use features from any of these independent layers, how might this system behave? What might the accuracy or performance look like? What might the search score look like? So this is just a super simple example. Another example I'd like to show you guys has to do with, yeah, go ahead. Mm-hmm. Yeah. So that's a really, really good question. And so in this case, there's no learning component to this application. And so for this specific problem, what we really need is we probably need to train the model just once. I mean, we can update the model, but for the sake of the functionality we're interested in, the model doesn't need to be continuously trained. And right now, it's in that phase that I mentioned earlier called the prediction phase. And so earlier I told you that the model would typically go through a training phase, a test or evaluation phase, and then the prediction phase. And so learning mostly happens only in the training phase. And so right now, we just have a model. And what's happening is that for all the images in the data set, we already have computed these embeddings for all of them. So we have that stored in some database. So what happens is that when we get a new image, we get the model to give us embeddings for this new image, and then we compare it with all the other embeddings in our data set, and then we can then rank all of these images in the data set based on some distance score. And then let's say in this case we showed the top 15 results, and that's how we get this functionality. And so at no point is the model updated here. However, maybe we might say, oh, the sort of data in our database is changing, and maybe we are monitoring performance and we see performance is sort of degrading. And so maybe we might decide that every month we need to then collect some new data, label them, and then train or update this model. Does that help answer your question? Yeah, and that was a great question. If anyone has any other questions, please feel free to interrupt me at any time. Another example that I'd like to show you guys is something called handtrack.js. And so, and this is a demo that I built just to demonstrate how you can use a neural network model to sort of track hands or gesture in image. And so the one interesting thing about this is that the entire thing runs in the browser. And so it means that it demonstrates some of the power of TensorFlow that I mentioned earlier, in which you could train a model in Python and then export a version of it in JavaScript and then get it to run in the browser. And so in this case, if we select an image, then this model can then figure out, draw bounding boxes around the hand and faces as they occur in the image. And in addition, it can also add labels. So for example, if the hand is closed, there is some sort of tag that says, okay, this bounding box is a hand, but the hand is closed. If the hand is pointing, there's all these different parts. And I think, assuming everything goes right, if you can see my screen, this is running live. And so for example, if I raise my hand and then I point, you can actually see that like it is tracking my hands in real time. And as I point, as I uh, make different gestures, you can see that the tag is sort of changing, that sort of thing. And this is something that you can try. You don't need to install anything. It's all run in the browser. You can always try it and just to get a feel of how well neural networks work. And so I'll also put the link there in the chat. Of course, it might differ. So, for example, it runs very fast on my computer. If you're on a mobile device, it might not run. If you're on a fairly slow computer, it might not be as fast as it was on my computer. But I think at the end of the day, it's still a good demonstration of how neural networks could be exported and then run efficiently in the browser. Okay, so I guess back to the original presentation. Let's see. So I mentioned earlier that TensorFlow has this multiple APIs, and the first API is the Keras API, and that's the one that I sort of recommend that you try out if you're sort of learning to use TensorFlow. And even within the Keras API, there are 3 ways to build your neural network. So the first is using the sequential API. And so this is sort of easy to use in the sense that you can think of representing the layers in your neural network as just an array of layers that you specify in Keras. And so this is the easiest one to use. There's also the functional and subclassing API, but it might be a bit complex for a starter. So far, I mostly use the sequential and functional API. So in the next slide, I'll talk a bit about the sequential API. So if you remember this little single layer neural network that I talked about earlier, how might we implement something like this in Keras? And so it's pretty straightforward. So we will import TensorFlow, and then we'll import layers from TensorFlow.keras, and right here, we will use the sequential API. So we'll call tf.keras as sequential, and essentially we just have an array full of. In this case, we just say we want a single dense layer, and it has just one unit. And so in this case, we have units equal to 1 because we have just a single output. If we're predicting more things, let's say 2 outputs, in the case of cat versus dog, then we might say units is equal to 2. And then after that, next thing is the compiled model. And then we'll specify some parameters, hyperparameters. And so for example, a learning rate. We'll specify a loss function and then some metrics that we want to compute. And I know that I'm skipping over the details of, for example, what is an optimizer, what is the loss function, what are metrics. And so at the end of the presentation, if anyone wants me to discuss these topics more, just let me know. But you can think of these as parameters of your model. The third thing is, once you're done specifying the parameters, you can then call model.fit, and this is how you train the model pretty much. And so model.fit takes in a few arguments. So the first is your data. So it's properties of your data. In this case, it will train features will be, let's say, some sort of representation of your images. And then labels here, in this case, if you're looking at the cat versus dog problem, then it will be a list of numbers. Let's say we say 0 corresponds to the cat and 1 corresponds to the dog, and we just have that, and then we'll call model.fit. And like magic, this process essentially takes an initial model that has random weights, and based on the trained data and the labels, it updates these weights, the parameters of this model, such that at the end of this process, whenever we get this model to predict, it is very likely to correctly predict cat from dog. And I'll go into, I've written some code which I'm gonna share with you guys at the end of the talk. And so I have some code that I've written, and then we'll walk through that code and see what it does. And so I want to walk through the presentation first before I actually start going through code. And so if you feel like, hey, it's going too fast, don't worry. We'll go to Collab and essentially a Python notebook, and we'll walk through some code. So the next thing I want to talk about is TensorFlow Hub. Some of you might have heard about it. It's a repository of trained machine learning models that are ready for fine-tuning and deployment anywhere. So it turns out that there are a set of machine learning problems, and a bunch of really smart and generous people have spent a lot of time training models to solve those problems. And they have taken those models and they have put them in some repositories such that if you're interested in solving any of this sort of problems, then you can reuse those models as opposed to trying to train one from scratch. And this is a really good idea, because to train a model from scratch, sometimes you might train a model for like 2 weeks. The model is training. Sometimes you need hundreds of thousands or millions of data points, and you need a really powerful and memory-intensive machine to do this. And so having pre-trained models just means that now you can use the power of all of these models without having to pay the cost of training the model yourself. So TensorFlow covers like problems in image space, so problems that deal with image data, problems that deal with text, video, audio analysis. So you can find pre-trained models for problems in all these data domains. In addition to that, these models can work very well within the broader TensorFlow ecosystem. And so if you wanted models that deploy to the web in JavaScript, so these models, you could get TensorFlow JS models. You could get TensorFlow Lite models, which is TensorFlow for mobile devices. You could get TensorFlow Coral, which is TensorFlow for small embedded devices like the Raspberry Pi or the Google Coral device, which is also some small embedded computing platform. And then also, there's also the TensorFlow extended ecosystem, which helps to sort of define pipelines, complex production pipelines for you to solve problems at scale. So all of these models from TensorFlow Hub, they work in all of these different areas. And so this is like a screenshot of TensorFlow Hub. I think you can just search for it on Google. You can navigate it. It's a really great place to sort of poke around. And so let's imagine that like we wanted to reuse some of the TensorFlow, from the models from TensorFlow Hub. What does that look like? And so it's as simple as defining imports TensorFlow Hub as hub. And so just for background, this is all Python, and we'll get to some code in a little bit. And then this is how we instantiate a new model from the TensorFlow Hub. And so we say hub.keras layer, we give it a URL. In this case, we are looking for a model that classifies birds. And then we can then get this layer. Then once we have that, we can then run classifier on images. So let's imagine that we have some images. Let's say it's in some format. Maybe it's an array of NumPy. It's a NumPy array. It contains vectors for all our images. We can then say get the probabilities. And then based on these probabilities, we can get the prediction with the highest probability. So when we build classification models, usually our output will be in terms of probabilities. And typically the output head or the output location with the highest probability indicates the right class. And then we can then get the prediction for that. Another use case. Go ahead. Mm-hmm. Mm-hmm. Right. Yeah. So that's a really, really good question. And so I think what you're referring to is something called type ahead. So, for example, you start to type a query, and um, and then and then I think Google populates all of the text or maybe previous queries that might be similar to what you're typing. Um, so the technical implementation for type ahead may not exactly use machine learning. And so in some cases, imagine that like Google has like a couple billion examples of queries that people have typed and they know which ones people sort of have clicked on. Then as you type your query, you could do a really fast match, token match between what the user's typing and all of the things that are in the database, let's say given, and this search can then be further qualified given, let's say, what you're trying to search for, your profile, all of that. But it could just be a database lookup. However, there's a version of that problem that would work quite well with machine learning. And so, for example, again, it's related to semantic text search. And so the problem is given two pieces of text, which might be um, expressed in with completely different vocabulary, which is quite common in English. So two sentences can mean the same thing, but they use completely different words. But at the same time, you want the model that, like, let's say, given these two pieces of text, you want this model to figure out if they're similar or not. And you can use that to also build some sort of search system too. And I say, for example, you have a database of, let's say, you have maybe titles of books, and maybe you start to describe a book, and you want this web application to show all of the books that might be related to this text that this user is typing. And so the good thing about using a semantic search model, a neural network model, is that the user might describe this book using words that don't exist in the book titles. So for example, it might be a book around, let's say, the Crimson, maybe the title of the book is The Crimson Sun. And so a user might come and type something like The Red Sun or The Red Sky or The Red Sky or Red Sky Rising. And so a good neural network model should figure out that crimson, the word crimson, is similar to red, and the word sun is similar to sky, and should be able to find these two different texts and then show that. And so to cast that problem, so you would cast it as a similarity problem, and what you need is a model that gives you embeddings or semantic embeddings for text. And in that case, you could also go to TensorFlow Hub and look at any of the text models and use those models to get embeddings. And then you can then use that in your application. Does that help? Yes, good. That was a great question. And so if we looked at the case of predicting crop disease, in this case, let's imagine that we have an image of a leaf. In this case, this is a cassava plant leaf. And we want to predict if this leaf has diseases or not. And so in this case, we can see these yellow spots on the leaf. It's indicative of some sort of leaf disease. And so we want a model that, like, if we gave it this image, it will tell us this thing has a disease or not. So how might we implement this using TensorFlow Hub? As usual, we will import TensorFlow. And then here we'll import TensorFlow datasets because it does have like this another resource in the TensorFlow ecosystem where you could easily import datasets that you might use for your experimentation. So in this case, we're going to import the dataset called beans. And again, this dataset is like a dataset of images, cassava, plant images in this case. And we might want to get some parameters like what are the number of classes. So in this case, I think this has 3 classes. I think either healthy, disease, or unknown, something like this. And then we might want to pre-process the image that we get. So in this case, we might want to resize the image. Can you guys hear me?
Yes.
Yeah. Okay, it looks like a few people in the chat are having difficulty sort of hearing, but let me know. Let me know if anything is going wrong. So might want to pre-process the image. You will see this typically a lot in machine learning where you take your image and you sort of normalize it using some denominator. In this case, it's 255. And also you might resize it. The main reason is because some of the pre-trained models would use from TensorFlow Hub. They have this requirement where the size of the input has to be fixed and has to be normalized. And so it just means that if you're going to reuse this model, then you need to, whatever images you're going to pass through this network, you need to sort of update it to fit the expectation of the pre-trained model. So once we do that, we then say, okay, we're going to map this processing function to our data. And then we're going to build a simple Keras sequential model. We're going to say, okay, we have 64 dense layers. And then we have a final output layer that, that corresponds to our number of classes. And so from this, if you remember later, I told you any layer between the input and output is called a hidden layer. So here we have one hidden layer that has 64 units. And then as previously, we compiled the model using a specific type of loss, a specific type of optimizer, and then we're interested in accuracy metrics. And then we can then run model.fit, which trains the model. So it turns out that if we do this, and if we use the basic ImageNet pre-trained model from TensorFlow Hub, we get about 48% accuracy, which is not that good. I mean, 48% accuracy is not that good. But the point here is that if we took this problem and we just used a pre-trained model on using a generic feature extractor like ImageNet. So ImageNet is not specialized to any specific problem. It's an ImageNet is a data set of over 1 million images across 1,000 categories. And I think this specific TensorFlow Hub pre-trained model is just based on the generic, just a feature vector from that, based on that generic data set. It's not tuned to any specific area. So we get 48% accuracy. The question is, can we do better? And so one way to do better might be to use, let's say, a pre-trained model that's probably pre-trained or fine-tuned on just crops or plants. And we can do that. So TensorFlow Hub has another model called feature CropNet. And so the thing that changes between the last one, if you see, I'm going to go to the previous slide. Here it says ImageNet. The next one, it says just CropNet, using the concat layer within CropNet. And so if we do that, use like a section of this model that has been fine-tuned on just crops or plants, then we get 60% accuracy. And then it turns out that CropNet also has a feature vector that has been trained specifically on plant diseases. And so in that case, it's cassava plant disease. And so it turns out that if we use this model, this feature vector that's even closer to our problem space. If you remember, our original problem space is to classify disease within the beans dataset, then we get even better accuracy. And so I'm sort of towards the end of this presentation, but I'd like to do a code walkthrough, just like I mentioned, and then we use the rest of the time to sort of ask questions, discuss your projects, that sort of thing. Let's see. Let me do a quick code walkthrough. So the first thing that I'd like to talk a bit about is just how might you implement a simple linear regression problem using deep neural networks in Keras. So the first part of this is just about getting a sample data set. And this is the data set that we have. And for this data set, what we have is the data set is about cars. And so we have things like the number of cylinders that the car has, its horsepower, its weight, its acceleration, the model year, was it from Europe, Japan, USA, that sort of thing. And we want to take all this information and predict how many miles per gallon this car sort of has. So, so essentially, when like imagine that if you're, and the idea is that let's say at prediction time, if we had all this information, we want to predict miles per gallon. So in this case, we would use like a TensorFlow sequential model. We have some layer called the normalizer, which just takes all of our data and tries to normalize it between a simple range, most cases 0 and 1. It turns out deep neural networks work a lot better if you normalize the range of the data that you feed through them. Next thing is that we are just predicting a single value. In this case, we're just predicting the miles per gallon. So our final output layer just has a unit of 1. And just like we saw in the slides, we can compile this model, and then we can specify a loss function and a metric. And so in this case, we are looking at a metric called MAPE, so mean average percentage error. So it means that like on the average across all our test sets, when we do like a prediction, what is the mean percentage of difference between what we predict and what the actual value is. And then it turns out that we can, when we run model.fit, which trains this model, we can get something called a history. So Keras sort of keeps track of the accuracy at each point during the training step. And if we run this, let's see. Okay, so TF is not defined, so we'll just run the notebook from scratch. By the way, are you guys familiar with Jupyter notebooks for running data science and programs? Hakeem, Jamali? Oh, wow. Well, sorry about that. I should have given an introduction. So essentially, a notebook, you can think of it like an interactive environment where you can write code. So for example, I'm using something called Collab. So you guys should really try it. It's a great way great place to sort of experiment. So go to collab.research.google.com. And so they have like free version. They have a free version of this thing. So essentially, think of it as just an interactive environment where you could write both code and text. And so in this case, let's say we want to write a simple print statement, hello world. We can run this thing. When we run it, we print to the console. Just pretty basic. And then we can have code cells that also help us write documentation. So if we delete this and we say we want to add like a text cell, maybe we can write some documentation and mark down this is in this section we train. Then you can run it, and then it becomes this little text cell that helps us document the code. So it's just a great way to write Python code and write documentation and run these things in parallel. It's a really, really great way to sort of structure your machine learning projects, especially when you're just experimenting. Of course, when you move things to production, you probably need independent Python files to sort of encompass all of your logic. But while you're experimenting, Jupyter notebooks are a great way to Jupyter. Let me just type that in, Jupyter notebooks. And blog.research.google.com is a great resource. So anyways, we can run each of these cells. So here we're just importing all the libraries that we need. You're writing some functions to plot some data. And then all of this code here is just to get some data, download some data that we need, normalize that data, convert it into train and test features. Sorry that I'm going through this very fast, it's just that I don't have a lot of time. However, the code for this, I'm gonna share it with you guys at the end so you can sort of walk through it. And so now that we have the data, we can then train a linear model, just like I explained earlier. And here we don't see anything on the screen because I've set this variable called verbose to 0. So it just means that like I tell Keras or TensorFlow not to print anything to the screen. If I change that to 1 and I run this thing again, we'll start to see some additional updates. So for example, it says that in round 1 of the training loop, loss is 98%. Loss is another word for error, and the mean average precision error is 98%. So like 98% of like this model is really, really wrong. So like 98% is wrong. But by round two, from 98%, this error goes down to 92. And you can just see that the error keeps going down. And so the model is making less and less mistakes as it updates its parameters until we get to a point where by round 130, the error is now down to 10%. The mean average precision error is down to 10%. I mean, if we train it longer, it might get even smaller. And so we can then plot these errors. And so if we did something like, there's this function I wrote earlier that says plot history. We can see that in round 0, the error was almost at 100%, and the error kept going down until we got to like this round 130 of the training loop. And so graphs like this are just a great way to figure out, oh, is my model improving? Is it getting better? And so just a good thing to do. Another thing we can do is that we can just write some code to sort of look at the percentage difference between the actual, so in a test set, the original miles per gallon and our predictions. And so we can look at all of that. So all of that being said, I also want to talk a little bit about TensorBoard. So TensorBoard is this really nice tool that you can use to visualize the progress of your model. So all of the code here just says that in this notebook, let's load the TensorBoard extension. Let's select the directory where we want to store the TensorBoard data. And then we'll define something called the TensorBoard callback, such that when we train a model using Keras, we tell it, okay, as the model keeps training, report all of the model updates to TensorBoard so we can visualize it. And here we're going to do the exact same thing we did before. We train our linear model, the exact same thing. The only difference now is that we've added this thing called callback. And so it just means that as the model gets updated, we should send all these updates to TensorBoard. So if we run this, our model is going to train again. And when it's done, we can then run TensorBoard to look at the visualization of what has just happened. So in this case, we're running TensorBoard. Yeah, now TensorBoard is running. And then we can see some interesting metrics. So first we can see the loss. Loss here also means error. And then we also have this other metric that we were interested in. And so we can also see that this metric is going down. If we wanted to add more metrics to this, so maybe we want to add mean absolute error, and let's say maybe some sort of, let's say maybe accuracy. Accuracy is not a good metric here, but we're just going to add it just to see how it's reflected in TensorBoard. So we're going to train our model again. And right now the model is training. And then we can go to TensorBoard and take a look again. Right. And so here we now see that because we added the new accuracy metric, we have that showing up on TensorBoard. We have our loss like before. Then we have mean absolute error. We also have that metric showing. Then we have mean absolute precision error. So essentially, as you add more metrics, because of the good integration between TensorFlow and TensorBoard, you can then visualize all of these metrics pretty easily with really good visualizations. Then the final piece I'd like to talk through is the example we saw earlier, where we tried to use a model from TensorBoard in order to classify a bird. And so in this case, we're just gonna download a bit. Okay, let's see. Yep. So we have a variable that has not been defined. So let's just define that in case we want to specify the size of the image. So now we're just gonna create like get a bird classifier pre-trained model. And now we're gonna download an image from the internet. Then we're gonna visualize this image. Okay, I'm gonna visualize the image. Here's the image of a falcon. We're gonna get predictions. And then we can look at the range of predictions across all of the classes that this model supports. And then more importantly, um, we can then try to figure out what exact what exact image what exact bird class that this model predicts. In this case, it predicts Falco mexicanus, which is a falcon, which is exactly what this bird is. And so that's just an example of how we might use TensorBoard. And then finally, if we're going to say, okay, we had this data set and we wanted to, and the example I showed earlier where we had the beans data set, and we're going to take a pre-trained model, and then we're going to train this pre-trained model using this new data set. And so it just shows how you can take a TensorFlow model and not only use it, but improve it to solve your task. So that's what this final piece sort of focuses on. So we download the beans data set, and then like we showed earlier, we will pre-process it, then construct a train and evaluation data set. And then we have this function to get a model from TensorFlow Hub. And next, we will then train the model. So essentially, once we get the model from TensorFlow Hub, we'll then call model.fit. So in this case, we have the model training. And essentially what you want to see is that you want to see that the loss of the error is sort of going down as the model is training. So it starts at 1 to 4, it's kind of going down as this model is getting trained. And so I think at this point I'd like to stop. I think we've walked through enough code. And I think here's a link to the notebook that I just walked through in case you guys want to try it on later. Put a link to that in the chat. So at this point, I'd like to, if you guys have questions, if you have questions, now is a good time to sort of ask them, and then we can conclude. Yes. Right. Say Java or okay. Yeah, that's a really, really good question. Unfortunately, really unfortunately, the two top frameworks for designing or creating neural networks, which is TensorFlow and PyTorch, they're both just Python only. There are some projects that have like Java bindings for building neural network models, but frankly, those frameworks are just nowhere near as well developed or as good as TensorFlow or PyTorch. And so typically I usually do not recommend doing machine learning or data science with Java. I mean, some people still do it. It's just that, especially if you're beginning and you're trying to learn concepts, and essentially you would need like tutorials and a really good ecosystem. And if you want a good path to production, especially if you're going to go to industry, Python really is the main language for that. Yeah. 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 Any other questions? Any other questions? So so the answer is yes. So the main benefit of understanding how like machine learning models work underneath is that your ability to debug these models is just a lot much more sophisticated when you know how it works underneath, right? So for example, while we were writing this piece of code, it could have failed for many reasons, right? And so in practice, you might see that, oh, as you train your model, your accuracy is not increasing, or I don't know, you're seeing like non values, zero values where you're expecting like integers or floats, or you're just seeing like very unexpected results. And so, in cases like that, maybe the reason is because I don't know, you haven't set your random initialization correctly, or there's some sort of I don't know back propagation issue that's specific to your data set, these sort of things. And so if you really don't know how the models work underneath, then your ability to debug this sort of problems, which tend to happen from time to time, can be severely limited. And so I guess for you guys who are starting out, it's good um, to invest some time to understand how these things work underneath. So for example, it makes sense to try to implement back propagation, matrix multiplication. Maybe even if you don't implement it from scratch in pure Python, maybe use a low level numeric computation library like NumPy. So implement neural networks in NumPy, that sort of thing, and just to build your understanding. And sometimes also at job interviews, especially for beginner roles, just to test your knowledge. Some interviewers might ask you to do this sort of tasks, and so from those two perspectives, is a good idea to sort of build your own understanding of how those things work. Number one is just good to demonstrate knowledge, especially during interviews, and number two, your ability to debug like models is a lot better if you understand how it works underneath. Any other questions? Uh-huh. Yeah. So I didn't really have enough time to go through the details of what we did in this second example, but that's sort of exactly what we're doing here. So in this case, what we're doing is that like we have a URL to where this function here just says that, oh, get a model from TensorFlow Hub. And so what it means is that we have a URL that points to the model on TensorFlow Hub. And then we are creating a completely new Keras sequential model, right? And this Keras sequential model has three layers, or three high level layers: 1, 2, and 3. Can you guys still hear me?
Yes, we're hearing.
Yeah. Yeah. So the first layer here, we construct this layer from a pre-trained model from the TensorFlow Hub. However, the other two layers, these are completely new layers that they have like completely random weights, and these are not part of the original pre-trained model. So we're just saying that the first layer in this our new neural network is from the TensorFlow Hub, but the next two are layers that we create ourselves. And so we can even, just for as an example, we can create an extra layer now. Say now we have this, let's say 32 units here. And then we can then say our final layer corresponds to the number of classes that we're interested in. And then when we run model.compile, we compile that. And then when we run model.fit, what exactly happens is that our input comes, it flows through this layer from the model hub. However, all of these different layers, we fine tune the weights of all of these remaining three layers such that they correspond to our exact problem. And so here we have taken the base model that we get from TensorFlow Hub, but then we have also tacked on three additional layers. And we also, when we call model.fit, we are updating the parameters of these three additional layers such that they correspond better to the problem or the task that we're solving given that data. And so this will be how you would implement that sort of, hey, if we have this model that like is related, let's say it's an image model, but maybe we're interested in something very specific. Maybe we're trying to predict if, I don't know, if maybe pictures of the roofs of houses contains damages or not. And so maybe we might not find a model exactly for that. So in that case, we can start with a pre-trained image model, anyone, and then we can add some additional layers. And then we can take all of our data of this new task, which is like roofs with labels. And then we can then set it up like this, where we train these new models, this new model with additional layers. But then these extra layers that we have are fine-tuned just specifically to our problem. So that'll be the way you implement something like that. Well, if there's no other question, I really hope this session has been useful to you guys.
I have a question.
Okay.
So, how do you go about determining how many layers you would need in your model and the activation function?
Right. So typically uh I usually okay, first of all, the number of layers and the parameters of these layers is more of an art as opposed to a fundamental hard science. And so, for example, um, as you get experience building these models, you start to build some intuition on what is the minimum that might be suitable to a specific problem. And it also depends on the problem, and it depends on whether you're using pre-trained model weights and all of that. However, the question is, if you make a decision, so in this case, here we've added these two extra layers. So the question is, do we actually need these two extra layers? Is it too much? Is it too little? And there's actually a hard scientific way to figure that out. And so you can sort of make an initial choice, and you can update these choices based on the result of the experiment. And so let's say in this case, we select, we choose to have two hidden layers, each 164, 132 dimension size. And we train the model and we see that we get, let's say, 90% accuracy. Next question is, do we add more? So you can add an additional layer. And most likely what you might see is that the performance doesn't increase. And so you know that like adding more layers doesn't really help. The next thing you can do is like, do I need this much? Because the more layers you add, the slower the model is and the more over parameterized it is. So the next thing you can do is you can remove the layer and sort of see, does my accuracy decrease? If it doesn't, if it's still 90%, then you figure out that, oh, the model additional layers at some saturation point. Up until that point, you don't need the additional layers. And the next thing you can do is, okay, if we delete this extra layer, do we still need 64 units here or 32 units here? And you can do this sort of experiment manually, or you could use something called hyperparameter optimizers. And so typically that's what you might do in production when you're actually building like networks to scale. You will use some libraries. There's some libraries. I think Keras has a version of that. Just search for Keras hyperparameter optimization. You can then give it like a range of numbers. So you can say, okay, train a set of models within 2 to 4 layers using layer depth between X and Y, and find me the optimal model. And so this will be how you would maybe navigate a design space, and find the most appropriate model. So hope that helps you.
Yes, yeah, that helped. On in terms of the activation function, like
Right.
what?
So yeah. So most of the time, for most problems, just within your hidden layers, in my experience, using a ReLU seems to work. And I think there's also a lot of research papers published in that ReLU activation functions tend to be the best. So for image problems and for hidden layers, so these are layers between your input and your output. For your final output layer, um, depending on the range of values you're interested in. So I think the default activation layer for your output for your dense layer, let's see, default Keras dense activation. Let me just do a quick check. Yeah. So Keras has a default activation layer. Anyways, for the output layer though, it depends on the range you're interested in. I think if your results should be between 0 and 1, which is closer to probabilities, you probably should use the default activation function. If you're looking for something, range for tan h. If you're looking for something, let's say between -1 and 1, you would use like tan h activation function, which is like the range of so a tan h function will give numbers between -1 and 1. And so just depending on the range of values you're interested in for your output layer, then you would use different activation functions. However, for hidden layers, typically, I think in most cases, you will get really good results with the ReLU activation function.
Okay, thank you.
Well, it's 2 p.m. my time. Unfortunately, I have to run to another meeting. However, if you guys have any questions, please feel free at any time to reach out on Twitter, or I don't know. You can get my contact from your organizers. And I look forward to really hearing from you guys.
All right, just before you go, Shannon, I hand over to you.
Okay, good afternoon, everyone. Can you guys hear me? Okay, so thank you so much again, Mr. Victor. Is it Dibia or Dibia? If I'm butchering your name, I really do apologize.
That's fine. Dibia.
It's Dibia. Okay. All right. So thank you so much for taking the time out to speak to us today. You have definitely provided us a belly full of knowledge, and I really do hope each and everyone present here with us was able to take something away from this presentation. I also wish to extend thanks to all the participants who were able to attend this session. I noticed that through the session, we were able to maintain about 20 of us, and from where we're coming from, personally, I believe this is a really good turnout. I feel like we need to have more and more of these sessions because, it kind of creates the space for growth and development. And we also get a chance to interact with each other, and that's a plus, A special thank also goes out to the Cursor Tech core team. The president, Jamie Lee Smith, our vice president, Sean Grant, the project manager, Hakeem Watson, Jada Walter, the club secretary, and Shaquille Barnett, the finance manager, for organizing this session. To me, I see Cursor Tech as more than just a club, but instead a movement. And with that being said, I can strongly say that this movement is led by a team of brilliant young minds whose aim is really just to create a space where anyone can join and learn a fair bit of IT skills, and we can use it in our everyday lives to our benefit. We learn something new every day. And I'm not sure if you guys are realizing the sign of the times, but IT skills, it's becoming it's a must-have requirement, and it goes right across the board, especially in the financial industry. Again, I really do hope to see more sessions like this in the future, as the club continues to grow, where we can just come together and we just learn, we interact, we inspire, and we encourage one another. And I really do encourage all the attendees that are present to take advantage of this opportunity that Cursor Tech is putting on. Not every day you see students readily willing to give back. So we really and truly need to big them up for that. Again, thank you so much. Again, Mr. Victor Dibia, for taking the time out. I am Shannon Taylor. Good evening, everyone. Be safe. COVID is still keeping, so I implore you guys to remain indoors if you can. You go out, you wear your mask, you use hand sanitizer, and you practice social distancing. I will now hand over to the project manager, Mr. Hakeem Watson. Hakeem, you there?
Shannon, I guess Akeem probably move away from his computer. So
Okay.
yeah, so if there's no more questions, then this is it for the evening. Yeah, basically that's it.
And I guess if you have any other questions, you can always just post it within the group.
Yes. Alright.
All right, then, guys, have a good evening. Thank you so much for having me.
Alright.
Thank you guys for attending.
Thank you.